when can I find n linearly independent eigenvectors in Rn if my matrix is an n by n matrix? So that's a transformation from Rn to Rn. Okay. When can I find n eigenvectors here that point in different directions? So one special case I think we talked about last time was when all the eigenvalues of this matrix are real and distinct, then we'll have, for each eigenvalue, you have an associated eigenvector, and those eigenvectors will point in different directions. That is the technical term for linearly independent eigenvectors. And when those linearly independent eigenvectors can be found, in particular, that will be the case if eigenvalues are distinct, although in other cases you can find linearly independent eigenvectors. In particular, in a case where the geometric multiplicities of all eigenvalues add up to n, then you can find n linearly independent eigenvectors. And when we do, we'll see how easy it is to compute the powers of a matrix, for example. So let's get started in this. Let's start with stochastic matrices today. So consider this matrix whose columns add up to 1. So here's a matrix. Let me bring the same examples I did in other sections. And actually, those were the ones that I included, I think, in the notes. So that should be fine, but let me find them. All right, so this is the one. So 0.8, 0.2, that's one matrix whose first column adds up to 1. This is called a column stochastic matrix. Has applications in probability, stochastic processes, various stochastic chains, and so on and so forth. So this column stochastic matrix, okay, both of these columns add up to 1. Okay, if you sum up the columns, they add up to 1. There are a few things to notice about matrices like these. Let's do a little bit of a review kind of thing. So suppose you have a matrix whose actually rows add up to 1. My claim is that such a matrix, so for example, let me transpose this matrix. I'm going to put 0.8, 0.2, 0.3, 0.7. So this is just this matrix transposed. So all the rows that we're laying down are now standing up as columns. Okay, so this row ends up as a column here. And conversely, all the columns here end up as rows laying down in this matrix and the other matrix. So it's just a reflection along the main diagonal. So I flipped the entries around the main diagonal. That's what it means to transpose a matrix. Okay, so this square matrix transposed has its rows now adding up to 1. And I'm about to claim that this matrix has an eigenvalue equal to 1. Can anybody help me out why there must be an eigenvalue equal to 1? And I admit this may be a slightly unfair question because it may be not that immediate to see it, but maybe, I don't know, maybe you can.
In this case, I would just try to do it at first. So that I do like a minus lambda I and see if it holds for the first case. And then,
Yes. Okay. Well, now that you mention it, okay, that's one way to do it. But then I don't know, would it be easy to generalize this? So the claim that we want to make is that if all the rows of an n by n matrix generally add up to 1, so these sum of the rows in each of the rows, the entries may be different in each row, but they add up to 1. We want to make sure that it has an eigenvalue equal to 1. It may be possible to go the way you suggested. It may be, it's also possible to do it just by working through the definition of what an eigenvector is. So if I'm to find an eigenvector, some kind of eigenvector, whose eigenvalue is 1, what I'm looking for is such vector x eigenvector, that when A is applied to it, out comes on the other side x itself. Okay, so this one has lambda equals 1. So in general, remember, finding the eigenvalues was to find lambda and x such as this holds. In particular, if lambda is 1, then this ax equals lambda x is just ax equals x. So is there an x such that when A is applied to it, it doesn't budge? It just doesn't change. It stays put. Is there such an x? For this matrix, is there such an x? For the purple matrix. I'm going to suggest 1, 1. What comes out on the other side? Because the rows add up to 1. you take one whole piece, and then take 0.8 of it, and then of 1, and then 0.2 of 1. What comes out as a result? The top entry. Is it going to be 1 for sure, because rows add up to 1?
Yeah,
And
they're
the second
both going to
entry
be 1.
Yeah, both are going to be 1s, right? So this 1, 1 is an eigenvector whose eigenvalue is 1. So do people see that I just got this satisfied, met? So 1, 1 is going to be an eigenvector, and lambda equals 1 is going to be an eigenvalue. Now, if a matrix A and A transpose have the same eigenvalues, they may have different eigenvectors, but they have the same eigenvalues. This is because A transpose minus lambda I, the determinant of this, and the determinant of A minus lambda I, those characteristic polynomials have the same lambdas as roots. So they will have the same eigenvalues. So this immediately implies that this guy will have eigenvalue of 1. Eigenvalue equals to 1 because its transpose had none, and the eigenvalues of A and A transpose are the same. So now I'm going to ask a question, like what happens if you apply A? So this is going to be my A, and I want to ask the question, what happens if you apply A to an eigenvector? Now this A may have different eigenvectors than this A here, the purple A, but let's suppose you found an eigenvector whose eigenvalue is 1. We know that such, okay, there's someone coming in. Did people sign in? So please sign in. Like, let's do this check-in. Let's end the check-in. Okay, so where were we? So what happens if you apply A the second time? So consider A squared x. So today we'll be computing these powers of matrices. So first we'll want to know what happens when you apply A the second time. So by A squared would mean A applied to the result of applying A to x. That's what it means to apply A squared to x. Okay, so
we already talked about it. We just taken an eigenvalue of an A, and the power of the eigenvalue will be the 2, whatever A power of n.
That's true. So let's see exactly so that everyone sees this. So A applied to x will give you x, right? Because of this, right? So now A is applied to x again. So what comes out on the other side is going to be x anyway, right? So when A squared is applied to it. Okay, now that I know that A squared x gets me x on the other side, what does A cubed x give me? That's A applied to A squared x, which I know to be x already, right? So that's AX, right? It's AX, and that's x again. So what comes out on the other side is going to be x, no matter what power of A I take. So A to the kth power applied to the same x is going to give me x on the other side every time if x is an eigenvector for lambda equals 1. We used lambda equals 1 here. So let's double check this on this matrix. So let me just give you its eigenvalues and eigenvectors. So let me copy this matrix here, the next slide. So this matrix A has, and by the way, the other eigenvalues will be in magnitude smaller than 1, in absolute value smaller than 1. This guy has positive entries. All of its eigenvalues will be 1 or smaller. Okay, so this has lambda 1 equals 1 with eigenvector. If you compute the eigenvector the usual way, you'll get one of those eigenvectors is 0.6, 0.4. And it has another lambda, which is 1/2. And the vector for that ends up being 1 minus 1. So let's double check that I didn't lie, that these were indeed the correct lambdas. So everybody's clear how to find them from our previous discussion. Can somebody briefly remind what the process is? So how did I find these eigenvectors?
So what you first did was you did A minus lambda I, then you solved for lambda, And then what you did was you plugged in those lambda values back into the matrix A minus lambda I, and then you saw what you got on the other side.
That's exactly right. Well, when we'll do another example today, we'll review that process just to make sure everybody's on the same page. But for now, that's exactly what we did. Well, actually, I plugged it into MATLAB and I got these numbers. Okay, and you probably have your favorite calculators, which you can bring on the exam, right? So let's say you find these eigenvalues and eigenvectors, and here they are. Okay, so now let's check that A applied to the first one, the one that corresponds to the eigenvalue lambda equals 1, is going to be 6, 4 is going to come out on the other end anyway. So if you just simply multiply this by 0.64, 0.6, and 0.4, you'll get 0.6 and 0.4 on the other side. So indeed, that's a check. And the check for the second one, when A is applied to 1 minus 1, what comes out on the other side is going to be the same vector. Well, what's going to come out on the other side? Can somebody help me out?
1, -1.
Yeah, so
Yeah.
that's true. So what's the multiple though?
1/2.
Yeah, 1/2 times 1 minus 1. So indeed, we've just verified that whatever our software gave us, those were the correct solutions. Okay, that's great. Indeed, that's fine. But now what happens if I apply a squared to 1 minus 1? That is when I apply A to whatever vector it is that comes out on the other side when I apply A to it.
You get 1/2, 1 minus 1.
1/2, 1 minus 1. So when I take this 1/2 out and apply A inside to 1 minus 1, and there's no doubt that what comes out is 1. So what comes out on the other side? What vector?
It'd be 1/2 squared.
Yes, exactly.
1 -1.
Yeah. So, and I don't think it's too much of a stretch to claim that when A is applied K times to this vector 1 minus 1, what comes out to the other side, if K is large, is just a 0 vector, right? You agree that when K is 1000, the right-hand side here is just 0. Okay, is 0, 0 for large K. My claim is now that any vector, so you can compute by using this, you can compute any power of A very, very easily. So for example, how can I compute A applied? By the way, how do I compute A applied to, say, let me take this vector, 0.8, 0.2. How do I compute this? If I know that the eigenvectors point every which way on the R2 plane, any vector like 0.8, 0.2 can be represented as a linear combination of these two eigenvectors. So it's going to be some amount of 0.6, 0.4 plus some amount of 1 minus 1. So what are the C and D here? You can find them easily. So if I take 0.2 of this and 1 of that, so 1 times 0.6, 0.4, and minus 0.2 times 1 minus 1. Do I get the same inside? The same vector inside? So I'm applying A to some new vector here, this new vector. So what comes out on the other side?
Wait, wouldn't it be plus 0.2?
Yeah, it's plus 0.2.
Plus 0.2, yes. Okay, so plus 0.2. So what's the vector that comes out on the other side?
0.8, 0.2. Oh, you on the inside, that's 0.8, 0.2.
Yes, so A is applied to that's how we took this vector. On the inside, that we decomposed that vector 0.8, 0.2 into some combination of the eigenvectors. Now, inside here, I want those eigenvectors because now I'm going to apply A separately to each one. So what do I get? When A is applied to the first piece here, what's the result?
You just get 0.64, 0.4.
Yeah, because this is an eigenvector for lambda equals 1. So no matter how many times I apply A to it, what's going to come out on the other side is going to be 0.6, 0.4. And here, what's going to come out on this side?
You would get like 0.1 times 1.
Yes.
1.
Let's write it down as 0.2 times 1/2. Okay, because why did I write it down this way? Because now I'll be asking you what's A to the 10th power applied to 0.8, 0.2.
It'd be 0.6, 0.4
Mhm.
plus 0.2 times 1/2 to the 10th
Exactly.
times 1 over negative 1 negative 1 the vector.
Do you see that as approximately the second piece goes to 0, right? And do you see that works out to 0.6, 0.4? So now all of a sudden, I know the result of applying the gazillionth power of A to this vector, 0.8, 0.2. In fact, the claim is that any vector on the plane, not just 0.8, 0.2, because it is some combination of these vectors here, of these eigenvectors, I can compute the result of applying the kth power of A to any vector x, because that x can be represented as a linear combination of eigenvectors, and I know the effect of A on the eigenvectors themselves. Does that make sense? Now, I want to, so maybe we'll return to this problem. Okay, so what is the question will be, what is the 1000th power of A itself? Okay, so let me slightly switch gears, no, although not completely. And let me, before I do an example, review a little bit of, let me ask you this. So what is A time, I'm going to take all the eigenvectors. So here's what I'm going to do. So let A be an n by n matrix that has, so it will have, and how many eigenvalues does it have? An n by n matrix?
Does it have n?
Yeah, it has n
eigenvectors?
eigenvalues. Now, again, some of these may be repeated, some may be complex, but you'll have n eigenvalues because the characteristic polynomial is a polynomial of degree n, and that will always have n roots. So let those be lambda 1, lambda 2, and lambda n, the n of them, and whose eigenvectors and eigenvectors associated with those eigenvalues. I'm not yet claiming that these will be linearly independent, but if they are, this will be the nice case. Even if they are not, I'm just going to write down the eigenvectors associated with these eigenvalues. Here's the eigenvectors are going to be x1. That's the first one for this guy. This guy has an eigenvector x2. It's a column. What's the size of this column? I'm writing these vertical bars, meaning just to indicate that this is a column.
Would it be
The
n?
length of the column you're asking?
Yeah,
N?
it's n, right? So
Yeah.
it's an n component vector, right? So we're going to put those columns and call into a matrix, and we're going to call this, so notation to denote by S this. Just simply taking each one of these eigenvectors and putting them into the columns, just putting them side by side, just tag them next to one another. And you'll have n of them. What's the size of this matrix?
N by n?
It's an n by n matrix because each column is n tall and I have n of them, n eigenvectors. It's an n by n matrix. And now here's my question. Okay, so, and also, I'm going to take these lambdas and denote by lambda this matrix here, diagonal matrix that has lambdas on the diagonal here, n of them. Again, this is an n by n matrix, and all the unfilled entries are zeros. So all the entries here are zeros. That's a diagonal matrix. Okay, so just notation so far. So all we did is we took the original matrix A, found its eigenvalues, and put them into a diagonal matrix like this. Okay, so set them aside, just leave them aside. Then I found the n eigenvectors, each eigenvector associated with the eigenvalue, and put them in a matrix that we called S. That's all we did. Now, here's my question to you. I want to decompose this. Okay, this is a bit of an unfair question, but let me ask it anyway. So AS. So what am I asking here, just to be clear? So I'm taking A and applying it to, when I
Your
apply it to the, yeah, sorry,
You're applying it to your eigenvalues of A?
eigenvectors, eigenvectors.
Oh, sorry, eigenvectors of A.
Yeah. Yes, that's correct, right? So if I just had not A of S, but A times X1, what comes out on the other side? What would be the answer to this? If I just had one column.
Would be lambda 1 x1.
Yeah, lambda 1x, right? That's just what comes out on the other. By definition, that it's an eigenvector, so what comes a lambda 1 times multiple of that eigenvector. I'm just simply putting them side by side into a matrix. That's all I'm doing. The second eigenvector, because I put it there in the S, what would be the second column of this matrix?
Lambda 2 x2.
Lambda 2x2, right? And if I put all these eigenvectors here, all n of them here in this matrix, what comes out on the other side is another matrix that is lambda times x of n, right? Now, this matrix, the last matrix here, actually, let's resize it here so that it's clear what we're doing. Okay, so here's my matrix. Now, here's what I want to claim, that this matrix can be written down like this. I can, again, separate my eigenvectors from the numbers themselves, from the lambdas themselves. I'm going to put x here, x1 here, x2 here, and xn here, again, separating them. And here, I'm going to have my lambda matrix, this guy. So I'm going to write down, I want to make sure that everybody sees that what I've written down, just algebraically, nothing else, is correct. So these are all the zeros. Do you see that if I multiply these matrices like that, this is my matrix S, and this is my matrix lambda. Do you see that this multiplication this way makes sense? So for example, if I multiply S by lambda, if the first entry here is, let's say, x11, the second entry is x12, and so on. When I multiply these two, don't I get this same matrix? So notice, so the first entry here is lambda x11, the second entry is lambda x12. What happens when I just multiply these two matrices, just the usual way, the way we know how to multiply matrices? Don't we take this component, multiply by this one? Then whatever is the second component multiplied by this second down the column, which is 0. Then I take the third component here in the first row and multiply it by the third one down the column, which is 0. So do people see that the product of these matrices is such that the first component ends up being exactly lambda times x11? Do people see this? What's the second component when I take the product of these matrices? What goes into the second component? Is it x12, the second? Now I'm multiplying the second row by the first column. What do I get here as an entry? Don't I get x12 times lambda 1 plus whatever the entry here is, question mark, non-zero entry, but multiplied by a 0 that comes below lambda, and so on. Because I have all the zeros down here, because of all the zeros down here, the first entry, the first column has to be the first column lambda x1. Do people see that? Okay, so if you see that, if you agree with this.
Wait, Professor.
Yes.
Is this big lambda matrix, is that just the identity matrix multiplied by lambda?
No.
Is that all it is?
By lambda, yeah, well, any matrix multiplied by the identity matrix is that matrix to begin with, any 8 you take. So if you take A, B, C, D and multiply it by an identity matrix, you will get A, B, C, D back, right? Any matrix. But here, I think the reason you asked this question is, well, here, okay, so this, do you agree that this works for any matrix? It's just what an identity does in the matrix. Here, these lambdas are different. So you have here something like 5, 1, 7. That's the way this matrix is. And yes, it is true. If you multiply this matrix or any other matrix, there's nothing special about this being a matrix of lambdas. Any matrix, including this one, multiplied by an identity matrix will give you back the same matrix. Make sense?
Yep.
But it looks like, but it's a good point that you're raising. So it looks like an identity matrix, except that on the diagonals, I have lambdas now this time. Right? Instead of ones, I have lambdas, but those lambdas are distinct. If all of those lambdas were the same, like they were 5, then you're correct. Then this would be 5 times the identity matrix. Then there would be something special about it. But then this 5 would be a number, and this identity matrix would be a matrix. And then what you end up with is 5, 5, 0, 0 here. Then those lambdas are just the same. Okay, so let me, so yeah, so good. So the point is that this lambda matrix just has these, like, all these lambdas on the diagonal, right? All these lambdas on the diagonal. But as the main point, do you agree that A times S has to equal S times lambda? So let me write this down. A times S equals S times lambda. All we did is just split the product here. A times S will split the product into a product of 2 matrices, like in a different way. Just because lambdas were eigenvalues and S had the columns of eigenvectors. This always works. Right? Now, so this always works. Always works, because I can always find n eigenvalues and some eigenvector corresponding to each of the eigenvalues. Now, although this works, we want to take it one step further. And for that one step further, we want to make an additional assumption that those eigenvectors, those n eigenvectors in the columns here, these guys that we found, are linearly independent, which in particular what will happen if all the lambdas are distinct, real and distinct, then you will get n independent eigenvectors here. And when you get that, independent eigenvectors, then this matrix S is invertible. Okay? But when we have n independent eigenvectors, vectors, then, okay, independent, then S is invertible because its columns are linearly independent. Invertible. And when this happens, I can multiply through by S inverse. So S inverse exists. Okay, so now let's multiply by S inverse. So I have AS equals S lambda. So I'm going to multiply. So let's call this inverse and make this purple. And S inverse exists. So I'm going to multiply from this side, both sides, by S inverse here. Right? What do I end up with here?
The identity?
The identity matrix. So do you see that then what we have is a special decomposition of A? We started out with A. That A is split into the product of these 3 matrices. It's a cute decomposition. If you can kind of find eigenvalues, so the one thing that is that it's cute, but it's also useful. So you see this, the decomposition works if S is inverse. If I have S inverse, then this decomposition has to work. This piece works all the time. It's just algebra. But if I can also invert S, then I'm multiplying through by this S inverse, and I end up with this fundamental equality of the day. Okay, so this is our decomposition of this is when we are able to do this, that is when S is invertible, we'll say that matrix A is diagonalizable. This is one way to diagonalize S, to diagonalize A, the original any matrix, n by n matrix A. Okay, let's do some examples. Let's put some numbers there. Is it clear, like the high level overview, what we've just done, where we headed? And now we also want to talk, why is this useful? Okay, so let's talk for a second before we get to the example. Why is this useful? Suppose now I want to compute the gazillionth power of A. Can I ask you, like, what's the second power of A? Well, what is A squared? So I'm taking S lambda S inverse. That's my first A. And my second A is the same thing, S inverse. Is matrix multiplication associative? What does that mean?
It is like you can get rid of the parentheses.
Exactly, exactly. So when you first go into like a math class and they start by making these dry lists, seemingly, oh, matrix multiplication is not commutative, it is associative, and they list a bunch of properties. They come in very handy throughout the rest of the course. So it's not that dry, really. It's okay. So basically, the whole point of that is that I can put the parentheses wherever I want to put them. In particular, I can get rid of them completely, but I can also put them here, these parentheses, at the end of the day, right? And what's this product?
The last one is inverse of S.
Sorry, what? Oh, yes. Thank you. Okay, so what's the product? That's inverse S. That's the identity, right? So do I end up with S lambda S inverse squared here? Because this lambda gets multiplied by this lambda and gives me that square. Does that make sense? Do you agree then that in general, I have that a to the kth power, no matter what integer k is, positive integer, I get S lambda to the kth power S inverse, because this process here can be repeated the second time if you do a cubed. Again, you cancel like s's, then you cancel the s's again, and you get this essentially, as you keep repeating this process. Now, this turns out that it gives us an easy way, whenever we can invert S, to compute the powers of A, because all we have to do is find A's eigenvalues, find its eigenvectors once, invert that matrix S, the matrix of eigenvectors. So find this lambda, find this S. Okay, this is some effort, but we found them. Then we expended further effort in finding S inverse, but we found these matrices. Now computing A to the kth power is a cinch. Why? Because first of all you have to do is multiply these three matrices, and computing lambda k. Why is computing lambda k is cheap? Why is it cheap to compute?
It's a diagonal.
Yeah, it's a diagonal matrix. It's a matrix like this. So what's the 20th power of this matrix? It's just the 20th powers of the diagonal entries, and these zeros don't go anywhere. They stay there. So to compute the power of an entire n by a gazillion matrix, I simply want to compute the powers of the guys that sit on the diagonal, like ducks. Everybody else is a zero. So just compute the powers of the ducks on the diagonal, and you've got the power of the entire matrix, if it's a diagonal matrix. So computing the power of a diagonal matrix, any power, is like very inexpensive, because you're just raising a number to some power 1,000 times or a gazillion times, fine, but just a number you're raising to some power. Okay, now we're ready for examples finally, okay? So let me take again the example that I did in the other sections, because I think I'll post this video. So the example, again, I think that's the one from the notes. I'm pretty sure, but I think I'm sure. Okay, so here's the example. Okay, let me copy this thing as a cheat sheet. That's the first cheat sheet. This is the second cheat sheet. And finally, we're ready for the example of the day. Okay. Okay, so now A is this matrix. Where is the matrix? All right, so 1, 5, 0, 6. The question is diagonalize this matrix. Now, granted, this is the first example, it's a small one. Okay, but let's go through the process that we just described in symbols and in words. What's the procedure? First, find the eigenvalues. So first find the lambda matrix. What's in the capital lambda matrix? What's in that lambda matrix?
The eigenvalues.
The eigenvalues. For an upper triangular matrix like this, 1, 5, 0, 6, where are do I really need to compute the determinant of A minus lambda I, or can I just tell just simply by looking at it, tell what the eigenvalues are?
Since it's upper triangular, you can just tell.
Yes. Well, what are they?
Would it be 1, 0 and 5, 6? Or
no eigenvalue? No. Those okay.
Eigenvalues?
Yes. And the eigenvectors would not be the columns. Eigenvectors would not be the columns. Glad you raised that point. We'll find the eigenvalues in a second. Actually, no, I'll just tell you what the eigenvectors are and we'll verify that they're correct. But the eigenvalues, where are they?
They're 1 and 6.
Yeah, they're sitting on the diagonal, waiting for you to just be read. Okay, so the eigenvalues here are going to be 1 and 6, right? Everybody agree?
Yeah.
Okay, so let's find the eigenvectors now. Then I'm glad you brought up that point. So now eigenvectors. So let's just for practice, I could just simply tell you, but let's just find the eigenvectors. Let's start with lambda equals 1, the eigenvalue. So what do I write down? Matrix?
1 minus lambda, 5, 0, and 6 minus lambda.
Yes, but lambda is 1. So 1 minus 1.
You get
Yeah,
0, 5,
so 0, 5.
Yeah, everybody agree that I have this matrix. I'm looking for the null space of this matrix. That is, I'm looking what x's solve this system of equations. Is it really a system? What do we mean by a system? Yeah, it's a system of 2 equations, but one of those is redundant. Right? So what x's solve this system? So what's the solution? The solution is an eigenvector. The solution to this ax equals 0, what's in the null space of a minus lambda I? Eigenvectors are for that lambda. Anything that's in the null space is an eigenvector. So what's the solution? What's the pivot?
Would it be
1?
Yeah, I'm sorry, what's the pivot?
The pivot is the 5.
Yeah, the second column is the pivot column.
Yeah,
Right.
but the answer is a 1, 1.
Oh no, 1, 1. Will 1, 1 solve this? So you should always check. Like, let's say you think that it's 1, 1 is the
I'm sorry,
solution.
1, negative 1.
Okay, will 1, negative 1 solve this? So is 0, 5 times 1, negative 1? Will it give me 0? Right. So what's the usual procedure of finding what's in the null space of A? Pick a free variable, set it to 1, and determine what the pivot has to be. What's the free variable here? You just told us. What's the free again? The first column is the free. X1 is free.
X1, yeah.
Yeah, the free. So set that to 1, and then determine what does pivot have to be. If this guy is 1, what does the X2 have to be so that I get a 0 here? So 0 times 1 plus 5 times minus 1 did not equal 0. But I did set 0 times 1, this 1, I set it here, that's my x1. Plus 5 times something, I want this to be 0. What that something have to be? It has to be. The only thing that the something can be is 0, so that this works out to 0, right? So 1, 0 is the solution. Do people see this? The 1, 0 is the solution. So do you see that this is an eigenvector here? Is an eigenvector. Okay, so here I'm going to be writing down my S matrix, which has the first eigenvector down its column. And I just found the first eigenvector. Now I'm still looking for x2. This I don't know yet. I will erase this unknown and put the second eigenvector as soon as I find it. And I'll find it with your help. And this is good practice for finding the null space of A, because what we're doing when we're looking for eigenvectors is we're looking for the null space of a matrix. Which matrix? The matrix A minus lambda I. So let's find it. So let's find the second one. So let me make this guy smaller. Now we found this one for lambda equals 1 is an eigenvector. So that guy, we found 1. And for lambda equals 2, I'm sorry, lambda equals 6, what am I solving? A minus lambda I, what's that matrix?
It'd be negative 5, 5, and then 0, 0.
Negative 5, 5, 0, 0. What's in, okay, does everybody agree? I subtracted lambdas off the diagonal, leaving the off diagonal entries alone. So what's in the null space of this matrix? A minus 6i. That is, which non-zero x's are in its null space, meaning those non-zero x's will be the eigenvectors. So, yeah.
Wouldn't the solution be 1, 1?
Yeah, the solution will be 1, 1. Does everybody see that the solution is 1, 1? How did I figure it out? Just
You
by
said
looking
the-
at it, but yeah.
You set the free variable equal to 1, which is the second column, and then you can
Uh-huh.
see when the equation would equal 0.
Yeah, that's exactly right. So 1, 1 works, right? 15, 15 also works. And that's this whole procedure, it will work no matter which eigenvector I pick. I'll ask you later why. What would have happened to our decomposition, this guy, if I had picked different eigenvectors? Turns out the answer is still the same. You're still decomposing A. I'll ask you why in a second, and not in a second, in 20 minutes. Okay, so I just found the second eigenvector. So can I put this into the column of this matrix S? So now I'll have my matrix S then, if I put 1, 1 there. We just found our matrix S. Just for completeness, what's our lambda? What's our lambda?
It'd
How
be
do I
1,
put this?
0, 0, 6.
Yes, so do I put 1, 6 like this, or why not like 6, 1 like this? I mean, those are eigenvalues. How do I know which order to put them in?
Based on the order you put the eigenvectors.
Yes, and that-
set S or matrix S.
That's exactly right. And that follows from the discussion we had when we're splitting the matrices. Okay, so but ask me if you need to further clarify why that's the case. But I put them in the same order as the eigenvectors. So the first eigenvector that went in here, this eigenvector, was the eigenvector for lambda equals 1. So I put a 1 here as the first column, in the first column, associated with this. And then these are 0 entries. So now I need S inverse. What is S inverse?
Would it just be 1, -1, and then 0, 1?
That's exactly right. Does everybody see that you can tell what the inverse is without doing too many computations, just by thinking what this matrix does? If not, if you're unsure, you have all you need at the test to double check your answers, right? So S inverse is that, right? Everybody's good with this, that's S inverse? So let's check. Check. Is A equal to S lambda S inverse? So is A, here's A, here's that, lambda, and here's my S inverse. That was blue. Is it true? So let's check. My A was 0, 5, 1, 6, right? Here's my A. 1, 6, 0, 5, 1, 6. Oh, hold on a sec. 1, 5, 0, 6. 1, 5, 0, 6. Does this decomposition work? Well, after what we've argued, it better work. So let's check. What's my S? My blue S is 1, 1, 0, 1. My lambda is 1, 6 on the diagonal and zeros elsewhere. And my S is 1, -1, 0, 1. So let's check. What's the product of these two matrices? So now let's practice without multiplying individual components. What does this red matrix do to a matrix when it's applied to it from the right? So the red matrix comes from the right. What does it do to the black matrix, the diagonal one?
Does it take the top row, multiply by -1, and add it to the bottom row?
Okay, good point. It operates on the columns, not on rows. But that would be correct if it came from the left, what you said.
Okay.
The
Right,
bottom row shouldn't change, right? 0, 1.
Yeah, the bottom row shouldn't change, so let's rewrite that. This one, right? No, well, why the row? I'm sorry. I'm again talking. So when the red column comes from now, the answer may have been that, but let's think through it in terms of columns. The red matrix comes from the left, from the right. like this. It stands to the right of the diagonal matrix of lambdas. So what it does is the first column, it doesn't change. So the first column better not change, but the second column is going to be the second column minus the first column. So here I'm going to have a -1, and here I'm going to have a 6. Does that make sense? If you multiply those matrices, you'll get that. But we just want to think through it in terms of columns. Okay, and now we have the blue matrix too. Here's the blue matrix. And what's the result of multiplying the blue with the purple one? Now the blue matrix. Yeah, that's right. So now the blue matrix comes from the left. That means that the blue matrix, the elementary matrix is the blue one, operates on the rows of the purple matrix. So what does it do? What does it do to the second row?
So this one, it takes the second row, multiplies it by 1 and adds it to the first row.
Yes, exactly. So here you have a 1, and here you have -1 plus 6. Let me write down as 6 minus 1. And I'm going to leave it, instead of writing down a 5, I'm going to leave it as 6 minus 1 here for a second. But you agree that the purple matrix in the end and the black matrix at the start are the same matrix, right? This equals that. That was like a check. It's the same matrix. Okay. Now I want to ask, so this worked out. So what this shows is that this decomposition here at the top works fine. So all our argument was not, like all this argument at the start was not in vain when we showed this decomposition should work. Now we're verifying it with the examples. Now I'm asking this, what is a to the kth power? I'm asking a to the 27th power. So I'm asking what is 1506 to the 27th power. Now in general, when I have a large matrix and a bunch of non-zero entries, this is difficult to compute. Very difficult to compute. It's a lot of computation. You remember from the start of the course, just squaring the two matrices by the straightforward algorithm. It takes on the order of n cubed to compute. There are newer algorithms that do it in n to the power of 1.62 or something. They brought it down recently. But it's still, it's polynomial. It's expensive. It's expensive to compute the power of a matrix. Okay, so, but with our S and with our S inverse, we'll do just fine. Because this 27th power is going to be the same S as before, multiplied this time by the 27th power of the lambda matrix inside, and then S inverse is the same. But I already computed S and S inverse, so this shouldn't be difficult. So let's see. Is it going to be the same as my S matrix 0, 1, 0, 1? What's my lambda matrix to this 27th power? This is our lambda matrix here. What's the 27th power of this?
It's just
S is not
1,
0, 1, 0, 1. It should be 1, 1, 0, 1.
Oh, yes, of course, you're correct. Yeah. Okay, and how about the red matrix? Thank you. How about the red matrix? Now let me write down quick. 1 minus 1, 0, 0, 1. Agreed? Okay, so let's compute the result then. So I have 1, 1, 0, 1. And what's the result of multiplying these? Help me out, we just did this. So let's do it again, just for practice, for the final. Just drills, this is just a drill. So what happens to the first column stays the same, right? So here I have 1 with a -1 here. Okay, so do I have a -1 here?
Yep.
Yeah.
Okay, so that was the mistake. So I put it in the wrong place. And here, what do I have? 6 to the 27th?
Yeah, it's still.
Okay, great.
I just said it backwards.
Yeah,
We're gonna
okay.
type like 6 to the 27 minus -1 for calculating this matrices.
Sorry, one more time.
We have to type like did you type before? We have to do it for these matrices right now because
Yeah.
the 1, 1, 0, 1 is on the left side.
Yeah, yes. Now we're manipulating the rows, though, right? With the blue matrix. So Okay, so what was the answer then? So does the second row change?
No, so this one is 1, then 6 to the 27th minus 1.
Yes, yes. So now I'm adding the second row to the first, and I get this result. Okay, so that's the answer. That is the answer. This is a to the 27th. When you take this guy to the 27th power, this is what you should get, right? So what was the effort? The effort was in computing the eigenvalues and eigenvectors. Okay, granted, this was a small matrix. The eigenvalues were confined right away. Eigenvectors were not that difficult to find, but that's the effort. Let's do one 3x3 example before we finish up. So let me bring again the same. What example do we have? Something whose determinant is easy to compute so that we don't get bogged down in computations. Here's one. A is okay. Looks like it might be difficult because it doesn't have 0 entries, but this turns out to be simple. 1, 2, 2. So let me just tell you what the results are here. So the lambdas that work here, the lambdas are, what's the characteristic polynomial? I had it somewhere. Blah, blah, blah. Do I have it in here? Yeah. So lambda minus 5, lambda minus 1 squared is the characteristic polynomial. When you, this is the determinant, the usual procedure of a minus lambda I. When I compute this, I get that the factor, the characteristic polynomial, this is what I get. So the roots are lambda equals 5. Okay, that's root number 1. And then I have two roots. So of lambda equals 1. So for lambda equals 1, the lambda has, what's the algebraic multiplicity of lambda? Help me out. Because it has the second degree with which it goes into the polynomial.
It would be 2.
2. The question is, now we're in the danger zone. Because when we get the algebraic multiplicity of 2, I may not be able to find two linearly independent eigenvectors associated with it, right? For lambda equals 5, there is no problem. I plug in lambda equals 5 into a minus 5, so a minus 5i. That would be an easy case, okay? So let's start with a. Let's find the eigenvector associated with a minus 1 times I. What do I get? So I'm looking for eigenvectors now. So, and I'm hoping that I can find two linearly independent eigenvectors. So looking for eigenvectors. Vectors. So what's a minus lambda I?
It would be 2, 2, 1, 1, 2, 1, and then 1, 2, 1.
1, 2, 1. Let me write it down just like that. And that is going to be 2, 2, 1, 1, 2, 1, 1, 2, 1. Is that right? Did I get the wrong matrix to begin with? What is my matrix A? I lost my matrix A. You know what? I wrote down the matrix the wrong way. This was supposed to be 2, 2, 1, 1, 3, 1, 1, 2, 2. Now, with that, sorry, do I end up with this? Okay, so that's my a minus lambda I.
Wouldn't it all be 1, 2, 1s?
No, the first one.
Oh, yeah, yes.
1.
Yes. Okay, so that's what we should get. And now finally, okay, so now comes the question. So here's why. So for lambda equals 1, which has multiplicity 2, mult 2, I'm hoping to find two independent eigenvectors. And in this case, I can. Why? Because when I'm solving for a minus lambda I times x, that is what's in the null space of this matrix, right? So when how many equations do I really have? Yes, I know that there's 3 equations, but how many equations that matter do I really have?
You just have 1 because
1.
the other 2 just become zeros.
Exactly. So this is my system, so-called system of equations. It's just one equation. And this system of equations, what's the solution to it? Okay, so glad this came up because now this is practice. Now this is 0. It's a matrix whose single component is 0. So let's just write 0 for that. 0. So this is one equation 0 on the other side. Okay, so how many solutions will I have? So
I'll have
again,
two
just
solutions.
spoiler, yes. Sorry, I didn't hear.
2 solutions.
Yes, I'll have a plane of solutions. I'll have the so-called 2-parameter set of solutions. I'll have a plane of solutions. Why would I have a plane of solutions? Because how many free variables I'll have as many parameter family of solutions as I have free variables. So these are free variables. And this guy is the pivot. Okay, so now help me write down the plane of solutions, the 2-parameter family of solutions. Solutions. All solutions. How do I write down all solutions? I pick 2 special solutions by setting the free variable, one of the free variables, the purple ones here, to 1 and the other to 0. So just a reminder, these were x2 free, x3 free. These guys are set here, and I set them one at a time, as we always did, like this. And the pivot, x1 is the pivot, goes here, and that pivot is, well, determined depending on what the free variables are. So what's the first pivot here?
Would be -2. Yeah.
-2. And what's this pivot here?
-1.
-1. These are special solutions, special solutions to a minus lambda I x equals 0. Special 1 and special 2 is that. And what is the whole 2-parameter family of solutions? How do I write this down? The plane. C times this plus D times that. But a more algebraic approach would be, okay, so you write down as x2 times that plus x3 times that on the quiz. Any way you write it down, as long as it's a 2-parameter family of solutions. Anything on that plane, you vary x2 and x3, you get some vector on the plane that's embedded in the 3-dimensional space. This gives a plane. It's a parametric representation of a plane, this whole thing. Okay, so we have all the solutions. What's my matrix S then? Okay, these are the 2 eigenvectors here. And then, okay, I didn't tell you what's the eigenvector for lambda equals 5. We all know how to find it. So let me just find if I have this somewhere in the cheat sheet, and I'll tell you what the answer is. For 5, we get 1, 1, 1. Apparently that's simple. Eigenvector, that was good, has eigenvector 1, 1, 1, apparently. So with this in mind, now this doesn't fit on the same page, so let me just copy this guy was for lambda equals 5. Okay, so this guy was for lambda equals 5. And these 2 were for lambda equals 1. So what's my matrix S? So S equals, and here's my lambda is going to be here. Let's write down the lambda first. Lambda is going to be 5, 1, 1. Agreed? The off entries are going to be zeros. Okay, so unfilled entries are zeros. What's S? Is it going to be 1, 1, 1 is going to go as the first vector in S, because my first eigenvalue is 5, and this is the vector for 5. Is my second eigenvector going to be the one associated with 1? Notice that I can then put these columns in any order I would please. That wouldn't matter because S inverse would be different depending on the order in which we put these columns. So in the end, everything will work out just fine. Just perfectly, everything fits together. So let's write them down as -2, 1, 0 as the first eigenvector, and the second eigenvector is -1, 0, 1. So this is S times lambda. What we have here is S times lambda is that product. So A then to the 50 gazillionth power, let's say A to 55, is going to be S lambda to the 55 S inverse, and is going to be, here's my S. I guess I'm rewriting it. Okay. So maybe this is faster than copy pasting sometimes. This guy is going to be 5 to the 55th power, 1, 1. And here I need S inverse. And yes, it is true. You have to compute this S inverse. So let me tell you what the answer will be if you plug it into MATLAB or compute it using Gauss-Jordan elimination. When you compute the inverse, anyway you compute it, you're going to get this guy. Again, this is S inverse goes right here. Okay, so -1/4. Here's like 1/2 -1/4. And here I have -1/2. And this is 3/4. That's just the way that this inverse works out. So the product of these three matrices is going to be a to the 55th. So my effort was in finding the eigenvalues and the eigenvectors. And then once I had the eigenvector matrix, finding its inverse. That was the whole effort. And of course, raising the diagonal entries to the 55th power. Everything else is 0. Not much effort at all. As long as I can multiply three matrices, I'm good to go in computing the 55th power of A.
Can we leave like this?
Yes, you'll normally it's understood that if the question, let's say you're working on a question like this, which you will have there, and you need to compute this inverse of a matrix, right? So it's understood that you're going to have some access to your favorite calculators somewhere. So you can always compute the inverse and verify what it is.
Can we use like a graphing calculator and just like input the, like, I think my graphing calculator has matrix functions.
Okay.
So we'll have to like use those for like.
Yes, you can use anything because the questions, you'll have a couple of questions on number crunching, but those questions you'll be asked to show the steps, right? So yes, bring your calculators to verify your answers, obviously, right? So you're allowed to do that because of the way we're doing this quiz around. Yes, so yes, you can use a graphing calculator. Although, what does it do exactly with the matrix function?
It can like compute inverses. It can multiply them. It can add them, stuff like
that.
Yeah,
you can use it if you have something handy that you like and it does the job, then you can use it. Or there are a bunch of like online calculators too, right?
Mm-hmm.
So if you have a long question that involves an inverse, yeah, obviously, so it's understood that you have access to a calculator like this, so you can come up with this one pretty quickly, right? And even if you will probably on a question, if it's a large question like 4x4 matrices, then you just leave it like that. No need to, the test isn't about like asking people to know how to plug in the numbers into a calculator and compute the results. Therefore, in addition to a few questions on number crunching, which you can always verify with a calculator, in which you will be asked to show the steps, you will have questions where you have to explain your answers, right? So and in those questions, you will be able to get partial credit, even if you get the wrong answer, as long as you clearly explain what it is that you are answering. So it's important to be clear in explanation. So please be like neat in writing up your answers, right? Just first make sure that in your mind it's clear, and then put it down on paper so that the other person on the other end can read what your thoughts were. That's one thing. So the questions, for example, instead of asking you, okay, maybe there will be a question like find special solutions to this, but the questions will be more along the lines of, so for example, here are the special solutions to a system of linear equations that were written down this way. What was the original system? Now you have to sort of go backwards and figure out, right? Rather than just plug something into a calculator and just get the answers. So that will, so as long as if you know how the calculator gets those answers, you will be able to solve these questions.